Hello and welcome back to PC Retro Programmer. In today's video we have a relatively straightforward task, but it's not obvious what the best approach is. In a recent video on the channel we wrote an interrupt-based timer which printed its output in hexadecimal, and the only reason we did that is because hexadecimal is much easier to work with on a binary computer than the ordinary decimal format that we're familiar with. It'd be really nice to be able to print values in decimal instead, and for that we'd need some code to convert from binary to decimal and then to print the result. And so that's what we're going to do today. In fact, we're actually going to print a value that fits in a 16-bit register, so it could have anywhere from 0 to 65,535 as its value. We're going to take a very straightforward approach of always printing 5 digits. So we'll pad with zeros on the left if necessary to make sure it has a total of 5 digits. So the value 0 would actually end up being 5 zeros when printed out on the screen. Now the most straightforward approach is to use remainder after division by 10, and to use this repeatedly to split off one digit at a time. For example, suppose we were trying to print the value 65,535, which is the largest value you can put in a 16-bit register. After the division by 10, we'd end up with a quotient of 6,553 and a remainder of 5. And you can see that that 5 is precisely the final digit of the number. And then we just repeat that process again. We'd use the processor division instruction to divide 6,553 through by 10, and this would give us a quotient of 655 and a remainder of 3, and that 3 would be the next digit of the number. And we just repeat this over and over until we get all 5 digits. Now there's a couple of problems with this approach. First of all, you can see that the digits are coming out in right to left order, and we want to print them in left to right order. Now this might not be a big deal. After all, we could just store all the digits in individual registers, but of course that means we'd need to use up 5 8-bit registers just to store all the digits. And the other problem's not quite so obvious. At first glance it seems like we could use 16-bit by 8-bit divisions, but the problem is that the processor 16-bit by 8-bit division instruction requires that both the quotient and the remainder fit in 8-bit registers. And that's simply not the case here. 6,553 is way too big to fit in an 8-bit register. So in fact, we'd actually have to use 32 by 16-bit divisions. And in fact, we'd need to do that twice. You can see on the first division here, we certainly need to use 32 by 16-bit division because the quotient won't fit in 8 bits. The second time we're similarly going to have value 655 for the quotient, which won't fit in 8 bits, and it's only on the third division that we'll actually be able to fit the quotient into 8 bits. So we'd actually end up with two 32 by 16-bit divisions and then a further two 16-bit by 8-bit divisions. And these division instructions are really very expensive, especially the 32 by 16-bit ones, well over 100 cycles. It could be 150 or even more. Now, another approach would be to divide by a large number first instead of a small one. And this has the advantage that you can get the digits out in the opposite order. So for example, by dividing first through by 10,000, we end up with a quotient of just 6 and the remainder 5535. And then we divide that through by 1,000, that would give us a quotient of 5 and a remainder of 535. And you can see we can just continue this and we get all 5 digits. And now the digits are coming out in left to right order. But we still have the problem that we have to use a couple of 32 by 16-bit divisions. In fact, in this case, the thing we're dividing by is 16 bits for the first two divisions. It's not until we get to the third division, where we need to divide by 100, where we can actually use a 16 by 8-bit division. So this is also not particularly efficient, and the best approach turns out to be to divide by an intermediate value of 1000 as the first step. So here we get a quotient of 65 and a remainder of 535, and certainly this won't fit in an 8-bit register, so that first step has to be 32 by 16-bit division. But after this, everything works in 16-bit by 8-bit divisions. Here we'd need to divide through by 10, and the results both fit in 8 bits. Here we'd need to divide through by 100, and the results fit in 8 bits, and then by 10, and the results fit in 8 bits. So we'd have one 32 by 16-bit division followed by 3 16 by 8-bit divisions, and this is cheaper. So that's the approach that we're going to take today. So let's take a look at the code that I've written for this, which I've called decimal.asm. First it'll do the conversion and then it'll print. By the way, for those who are a little bit more advanced, there is another technique which might actually do a little better. Instead of dividing through by 1000 on the first step, we divide through by some factor of 1000. Something that fits in an 8-bit register. So a good choice would be 250, and that would just leave a further factor of 4 to divide by, and of course division by 4 is just a shift right by 2 bits, which is exceedingly cheap in comparison to a division. So that first division by 250 would then be a 16-bit by 8-bit division. Now, the only problem with this approach is that for very large input values, dividing by 250 is going to give you something that doesn't fit in 8 bits. But it's not for that many values that you're going to have this problem. So what you could do is first of all check whether your input is small enough to use this trick, and then proceed that way if it is. And if not, just revert back to this technique 3 here. So if you're looking for a bit of a challenge, that might be something to give some thought to and see if you can make it work. Anyway, we're just going to use approach 3 here today. Now, the way I'm going to handle this today is first do the division by 1000, then split the quotient up into 2 digits and print those two immediately. And only after I've done that will I take the remainder, split that into 3 digits, and then print that. Now, the other thing I want to do is separate out the computation of the digits from the printing, because being able to convert from binary to decimal is already a useful function in and of itself without the printing. So it'd be nice for code reusability to make these separate things, the computation and the printing. But this means that I'm going to need a function for dealing with the first 2 digits and another function for dealing with the remaining 3 digits. And calling all of these functions is going to be a little bit expensive. So there's a way around this, and it's called macros. Now, in a way, a macro is kind of like a function in that in your main program, you just put the name of the macro that you want to call. You're really not calling a function per se. What happens is the assembler replaces that name. In this case, the macro has the name decimal top. It would replace an occurrence of that in your main program with all of the code that's in the macro body between the macro keyword and the end-m keyword. End-m just stands for end macro, of course. And this is a little bit like calling a function, but there's no actual function created and there's no call made. The assembler is just doing a textual replacement for you in your program. There are some downsides to macros, but they are generally faster than functions because there's no function call and there's no return. The other thing is, of course, you don't pass values on the stack typically. You just put values in the right registers to start with, and that may save you a little bit of fuss as well. So in this case, my decimal top macro is just going to deal with the first 2 digits and just the computation part. it'll take the initial 16-bit value, which we'll call n, in the range 0 to 65, 535, and it's going to assume that's in the AX register. It'll need to make this into a 32-bit value because the first division has to be 32 by 16-bit division. And then what it's going to do is divide by 1,000, and then it's going to take the quotient and it's going to split that into 2 digits, which is going to put into AH and AL. This is basically unpacked binary coded decimal format, by the way. And then what's left over, which we want to subsequently split into 3 digits, we're just going to leave that in the DX register when we're done. Now, as I said, the input at the moment is in the AX register, and we need to make it 32 bits, which means we need to zero out the top 16 bits, which for a 32-bit by 16-bit division is going to be in DX-AX. So here we zero out DX, which is the top 16 bits, and now we have a 32-bit value. And we need to divide by 1,000, and that has to go into another register, and I've decided to use BX for that. But I want to mess up as few registers as possible here, so I'm actually going to preserve the contents of BX with a push and a pop here, just like we do in a function call. But of course, there's no actual function call occurring. Now we just do the division. This is the 32 by 16-bit division. The quotient will be in the AX register and the remainder will be in the DX register. That's pretty cool because this function actually calls for the remainder to be put in DX, so we don't need to do anything more to deal with that. The only thing that remains now is to take that quotient and split it up into 2 digits. So it's currently in AX, and we need the 2 digits in AH and AL. And believe it or not, there's an assembly language instruction for precisely this. AAM, this takes value. It has to be a value in the range 0 to 99 for it to really work. And it splits that into 2 decimal digits, one of which it sticks in AH and the other in AL. That's exactly what we want. So that's all we need to do to deal with the computation for the top 2 digits. So that's what this macro does. Then we have a second macro for dealing with the bottom 3 digits. Now macros seem to be a pretty good deal, so why don't we use them everywhere if they're so much faster than functions? Well, of course there are some downsides, and so I should explain those. First of all, every time a macro is used, all of that code is expanded out textually behind the scenes. It doesn't actually happen in your text file. And this means that the program effectively becomes very large. That code will actually end up being output as machine code at every location that you've expanded that macro in your main program. And so this can mean that your final executable program can become very large if you use a lot of macros. So that's one reason they're not used very often. The other issue with macros is labels. So for example, you might need to jump to a label inside your macro, or maybe you have a loop and you need to jump back to the label at the beginning of your loop. And every time that macro gets expanded out, that same label name is going to get used. And that's problematic because the assembler won't know which of the copies of that label to jump to. So what it has to do is somehow or other distinguish all those labels. So every time the macro gets expanded out, you want the labels to be slightly modified so that they don't all end up being the same. And the way this is done varies from assembler to assembler, but in Turbo Assembler, it's done using the local keyword. Now, one of the bizarre quirks of Turbo Assembler is that you have to use the local keyword on the very first line of the macro. So you would put the word local here, all in capital letters, followed by a comma-separated list of all the label names that you're going to use in this macro. And then anytime it encounters any of those label names, what it does is append a little hexadecimal value to the end of that label name, which is different every time the macro is invoked. And so that means that all the label names will not be the same they'll differ each time you expand out the macro. So of course this is not a problem for us today. We're not actually using any labels. In fact, our decimal bottom macro couldn't really be simpler. As you can see, it's just 4 assembly language instructions. It's going to assume that that remainder that was left by the decimal top macro, it put it in the DX register, it's going to assume that that has at some point been moved into the AX register. And you'll see why that's not a problem a little bit later on. So in other words, this macro is going to assume that its input is in AX, and it'll be some value in the range 0 to 999, of course. And the job of this macro is to split that into 3 digits. And left to right, it's going to put them in the AH, AL, and DL registers respectively. Now, the first digit that we split off is actually the 3rd. So that's the one that we want to go in the DL register, and we do that just by a division by 10. So we put 10 in DL, and we do a division of AX by DL, and this will give us the quotient in the AL register, and the remainder, the digit we're after, is going to go in the AH register. Now we ultimately want that in DL, so we're going to have to move it there. So that's what this line is for. It moves that remainder from the AH register into DL, and so that's that digit dealt with. So the remaining 2 digits need to be split apart. The value is currently in AL, and we just use the AAM instruction again to split that apart into 2 separate digits. And one will go in AH and the other in AL, which is exactly what the description up here calls for. So that's all we need for our decimal bottom macro, pretty straightforward. So now let's take a look at a function for actually printing out all of these 5 digits, which is actually going to call first the decimal top macro and then print the values, and then the decimal bottom macro and then print the values. Now our print decimal function is a real function, it's not a macro, but we're never going to be calling this from a high level language like C, because that would already have its own decimal printing function. So because we're only ever going to call it from assembly language, we can dispense with some of the normal calling conventions that we have when calling a function from a high level language. So in particular, we'd normally pass parameters for the function on the stack. So we're not going to do that here. Instead, we're just going to assume that the value that we want to print, the 16-bit value, is already in the AX register when this function gets called. However, we want to be able to use this function pretty much anywhere in assembly language without messing anything up. And so because this function is going to mess up the AX, BX, and DX registers, I'm going to save those onto the stack, and I'll pop these back off the stack in the reverse order at the end of the function to restore the values back to what they originally were, so that nothing gets messed up. So this is what you'd normally do in a function, but you normally wouldn't preserve any of these registers. They're allowed to change. It's only certain registers that you'd normally need to save. It's just that I want to be able to use this anywhere without messing things up that I'm going to this trouble. Now, the first thing this function has got to do is invoke our decimal top macro, which will get the top 2 digits of our 16-bit value in the AH and AL registers, and the remainder, remember, it puts into the DX register. Now, in order to print the characters on the screen, I'm going to use the DOS print character function, and this actually expects the character that it's got to print to be in the DL register. And so that's not going to be very good if our remainder is in DX. So first of all, I need to save that remainder somewhere else temporarily. So I just put it in the BX register for now for safekeeping, and we'll pull it back out again when we need it, when we invoke our decimal bottom macro. So in order to print our characters using the DOS print character function, which is function 2 of interrupt 21H, it expects the character in DL, and at the moment the first character that we want to print, its value is in AH, and the second one is in AL. But at the moment, these are also not even ASCII character codes. These are just values from 0 to 9. So we have two things that we have to do here. First of all, we have to move the values into the right registers. So the way we can do that is to switch AH and AL around and then move AX into DX. And then the values that we want are in DL and DH. And then we need to convert those into ASCII codes. And the ASCII codes for the digits 0 through 9 are the codes 30 through 39 in hexadecimal. So what that means is we have to add 30 hexadecimal to each of the two values to convert them into ASCII. And so this just means that we need to add 30 to both DH and DL. Now we can call the DOS print character function first for the value in DL, and then we switch in the value that's in DH and call it again, and that's now our first two digits printed in order, the ones that came from decimal top. So now we take that remainder that decimal top gave us, which we stored away temporarily in BX, and we put it into AX, which is where the decimal bottom macro expects that to be. And that'll then get split up into the three values that we want for our digits. And we have to do the same thing again. We have to save the DX register because we need that. We then use exactly the same procedure that we did above to print the first two characters, which were in AH and AL. Then we restore our DX value back from where we saved it in BX. And then we print the third character, which is now in DL. First convert it to ASCII, of course, and call the DOS print character function again. And that's our third character printed. And then we just restore the register values back to what they were originally. Remember, you always have to pop these in the reverse order that you push them onto the stack. And then you return from the function, and that's all print decimal has to do. So now let's take a look at our main program, which is going to call this. And just for a little bit of fun, I thought it would be good to print all the values from 0 all the way up to 65,535 before finishing. Now, our main program is no mystery. It's essentially just a giant loop to iterate over all the values from 0 to 65,535 and print each one using print decimal. Now, that function expects the value to be printed in the AX register. So we start off by putting 0 in the AX register, and then each iteration of this loop, it's going to increment that value by 1 at the end of the loop, and if the incremented value is non-zero, it's going to loop back around to the start of the loop. So basically on the first iteration, it prints a 0, it comes down here, that gets incremented to 1, that's non-zero, so it'll loop around, and it'll keep looping around until it finally prints 65,535. That'll get incremented, and of course that causes a wraparound in the register back to 0 again. That no longer satisfies this condition, and so it falls through and the 0 is never printed, which is what we want. And so that'll be where the program ends. Now, the only other thing this needs to do is to print something in between all of the integers. Otherwise, they'll just be one after the other on the screen without even a space between them. So we're going to print a new line between each one. And to do this in DOS is a carriage return line feed combination. So the ASCII code for carriage return is 13 and for line feed is 10. And so we just use the DOS print character function twice to accomplish this. And so that'll put a new line after each of these integers that we print with print decimal. Now notice that we need the AX register for this, and of course AX is already being used to hold the values that are being printed by print decimal, so we'll need to save those values, and I'm just moving AX into BX to accomplish that, and then I'll just pull it back out again here after we're done with the new line printing. So that's all there is to our main program, and once the loop falls through, then it just waits for key press and exits to DOS. Now our main program doesn't start at the beginning of our code segment. That's actually where our print decimal function will be. So we need to tell it where the main program actually begins, and we do that by adding the name of a label to the end statement, and that label has to be at the start of our main program. So I just called this label start in this case for obvious reasons, and if we look up to the beginning of our main program, there's the label. So that's how it knows that this is where execution has to begin. So that's all there is to it. Let's assemble this and we'll run it, and I think you're going to be quite surprised at how slow this is. The main reason for the slowness is probably the DOS print character function, but we're also doing quite a number of divisions here which are no doubt contributing quite a lot to the speed. Now I've already run this through and it does indeed print all the values correctly, but we can actually stop it early by pressing Ctrl+C, and this should terminate the program whenever you're printing something on the screen.